Here is the question number 1.330 from Irodov from Hydrodynamics or Fluid Mechanics, and in this question it is given that a cylindrical vessel with water rotated about its vertical axis with a constant angular velocity omega. Find the shape of the free surface of the water, and in B the water pressure distribution over the bottom of the vessel along its radius provided the pressure of the central point along the central point is equal to P0. So let's solve this question for solution. Let us consider a small element of mass dm. So due to this mass dm, small fluid element, its weight will act downwards, so our weight force will be dm into g, will act downward. Now this is the normal reaction, and let this is the angle of contact theta. So this will be the direction of normal reaction n. If this is the normal reaction and this angle is theta, so this angle will be again theta. So if you divide this n into two components, then we will get this two component as n cos theta and another component is n sin theta. Now this is the direction of the centrifugal force. The centrifugal force acting on the small fluid element dm will be equal to dm r omega square. Now if we divide this dm r omega square into two components, then we will get dm r omega square cos theta in this direction, and another component will be dm cos theta and another component will be in this direction. So there will be a direction of dm. This is the direction of dm r omega square sin theta. Now if we balance this equation, then we will get from the FBD of this diagram, we will get n cos theta, n sin theta, n, there is a solution, n sin theta is equal to, as we are seeing, n sin theta is equal to dm r omega square, equal to dm r omega square. This is our equation number 1. Now we will consider the another component, that means n cos theta, which is n cos theta is equal to dm times g. This is our equation number 2. Now from this equation number 1 and equation number 2, if we divide this equation, dividing equation 1 by equation 2, this will provide us, or it implies, tan theta equal to dm r omega square divided by dm g. Now this dm will get cancelled. So after cancellation, we can write this tan theta is equal to r omega square divided by g. Now as we know, tan theta is a slope, so again this tan theta will be equal to dy with respect to dr. So if we cross multiply this equation, then we can write dy with respect to dr equal to r omega square divided by g. So y will be So if we cross multiply this, then we'll get dy will be r omega square divided by g into dr, or which is equal to omega square divided by g into r dr. Now if we integrate this equation both sides, now our limit of y equal to 0 to y, and our limit of r is 0 to r. Now if we evaluate the integration, then we'll find y will be equal to omega square r square divided by 2g. So now this equation shows an equation of parabola. Equation of parabola. So the upper surface of this curve will be a parabolic curve. Now we have to find the pressure. For finding pressure, this is our question number A, and in question B, dF, let us assume the centrifugal force dF, which is equal to dm x omega square. So from this equation we can write as dF equal to s into dp, which is again equal to rho s omega square x dx. So from this equation we can cut this s and s from both sides. So after cancellation we can write this equation as s dp, or we can cancel, if we cancel this, then we can write dp will be equal to rho omega square x dx. So if we integrate this equation both sides by taking limit p naught to p for the limits of p, and if we take the limit of x equal to from 0 to x, then we'll get p with upper limit p and lower limit p naught will be equal to rho omega square into x square divided by 2 from limit 0 to x. So if we evaluate this integral, then we will find p minus p naught will be equal to half rho omega square x square. So our equation for finding p pressure will be p equal to p naught plus half rho omega square x square. So this is our equation for finding the pressure variance with x axis. Now there are different ways of solving this question. So let us discussing an alternative way for solving this question. So alternatively we can write Bernoulli equation at, let this is our curve. So in this curve, let this is our point 1 and this is our point 3 and this is our point 2. So applying Bernoulli's equation at 1 and 3, then we'll get, so Bernoulli equation at the point 1 will be p naught plus, as the velocity is 0 here, so our rho v square will be 0, plus as the distance is the datum level, then we can write rho j is equal to again 0. That will be equal to p plus 0 minus half rho into x omega whole square. So from this equation we can write p equal to p naught plus half rho omega square x square. So this is our equation for finding the pressure variance due to rotation. We can also solve this question in another different way. So this is alternation 1, and the second alternative method is discussing below. Second alternative way. So for finding the second alternative, solving this question in another alternative way, so let us consider the pressure at this point 3 and pressure at this point 1 and pressure at this point 2. So from as we are seeing, the pressure at point 2 is equal to atmospheric pressure, and pressure at point 1 is also atmospheric pressure, because this both two are open to the atmosphere. So from this diagram we can write P3 is equal to P naught plus half rho omega square x square. So these equations come if we travel from 1 to 3. That means the pressure at point 1 is equal to P naught, and pressure as the distance from 1 to 3 is equal to R. So due to rotation there will be pressure difference del P equal to half rho omega square x square, that will be added with the term or the quantity which was in at point 1. Now if we consider point 2 and 3, as the pressure at point 2 is equal to P naught and we are traveling downward or at the depth h from point 2, then we can write P3 will be again equal to P naught plus rho g y, because y is the depth. So this is our equation number 1 and this is our equation number 2. So from these two equations, if we equate these two equations, then we can easily find the rho g y will be equal to half rho omega square x square, or we can cancel rho from each side. If we cancel the rho from each side, then we can write y will be omega square x square divided by 2g, or we can again write y will be equal to omega square divided by 2g into x square, omega square by 2g into x square. So this is the relationship between the x coordinate and y coordinate in our system. Again, we can solve this question in another different way also. So third alternative way is discussing here. Third alternative way. For solving this question in third alternative way, we will consider a rotatory frame. For a rotatory frame, the Bernoulli equation can be expressed as P naught plus 0 equal to P naught plus 0 plus rho g h minus half rho x square omega square. So from this equation we can cancel this p naught from the side, and after that we can write this rho g h will be equal to half rho omega square x square. Again we can cancel this rho from its side. If we cancel this rho from its side, then we can find h will be equal to omega square divided by 2g multiplied by x square. So this is our relationship for height and for y coordinate, means height and x coordinate. Now if we replace this h by y, if x equal to r and h equal to y, then we can write our equation will be y equal to omega square divided by 2g into r square, or we can write y is equal to omega square divided by 2g into r square. So this is our equation for locus. Again we can find the pressure in this way for applying the rotatory frame. For rotatory frame the Bernoulli equation will be equal to p naught plus 0 will be p plus 0 plus minus half rho x omega whole square. So from this equation we can write our pressure variation will be p equal to p naught plus half rho x omega whole square. So this is a complete solution for this question.